So essentially what we have done in this process is that we have reduced the problem of solving or approximating, I should say, not solving, approximating the solution of the Hamilton-Jacobi equation to solving this algebraic Riccati equation. Okay, so this is your algebraic Riccati equation, ARE for short. So you can solve this algebraic Riccati equation for a P. Once you get a P, then the value function, the optimal value function is simply given by phi transpose P phi. Once you know this V, then your U, the optimal U is given by minus partial V partial X times G. Okay? So that's the step. So you see the model is not explicit here, right? So and if you think in terms of data, the data that is being used is is needed to compute this phi, which are the principal eigenfunction. And if you recall, the way we compute the phi was actually we used the path integral formula. So if you recall that phi is of the form W transpose X plus H of X. So I'm writing it for the vector case. For the individual ones, it is of the form W transpose lambda X plus H of X, where W transpose lambda satisfies W transpose A equals lambda W trans, right? Which is the left eigenvector of this A matrix with eigenvalue lambda. And then the H satisfies partial H, partial X, F minus lambda H plus W lambda transpose Fn of X equals 0. Okay. So this was the so as far as the computation of phi lambda is concerned, I need to know the W lambda, which is the left eigenvector, which can be computed in data because it's just based on linearization of the nonlinear system at that equilibrium point. And H is found using this by solving at this PDE. I mean, I gave you one formula for finding this H in terms of the path integral, but if you look at it closely, this is again a linear PDE. And one of the way to actually solve this from data, or one of the way to actually get the H from the data, is again actually reduce this to a least square problem, because whenever you have a linear problem in infinite dimensional, after parameterization, you can reduce that problem. After a finite dimensional parameterization, you can reduce that problem to a linear problem or a least square problem in the finite dimensional space. So there are two different ways of actually solving this linear equations, infinite dimensional linear sets of equation for H. One using the path integral formula, and other is using the least square problem by assuming certain basis function. So in both the cases, we are using data, but we are not using the explicit system model. And in fact, we are nowhere constructing the explicit system model to find the value function. So this is what I meant by how to use the Koopman machinery to compute the optimal control by bypassing the explicit model. Okay. And the third thing which I said, I'll just say it. I may not actually have something to write, just because I think it is something which is perhaps one could write papers on, right? So what I said was that the way we do the Koopman currently, or the Koopman is used for control when you actually use data to construct the model and then use the model to design a controller. What is missing from that is actually you actually just collect data, and if you have nonlinear systems with multiple equilibrium points, you don't know what the model that you end up constructing from data is valid for which equilibrium point, or what's the region of validity of that model is. Okay, because if you're collecting data in only one region, then you may get a model which is suitable only for that region. Okay, and then when you design the controller, it may not work for the equilibrium point that you are really interested in. For example, stabilizing or doing optimal control with. So in the building of the model from the Koopman model from data, the explicit dependence or the explicit characterization of the validity of the linear model in what region the model will be valid is never really specified. Whereas if you look at this approach, the approach I just described you, where I actually tied the eigenfunction to a specific equilibrium point, this idea can now also be used in the formulation of the MPC. So what I'm saying is the following. Let's say I collect the data, but I'm cognizant of the fact that I'm collecting the data around certain equilibrium dynamics, whether it be stable or unstable. And now I use the data to actually not construct the Koopman model, but construct the principal eigenfunction. Now, the principal eigenfunctions could be constructed again by solving a linear problem. So rather than solving a linear problem to compute a Koopman model, I can solve a linear problem to compute the principal eigenfunction. Because I know these principal eigenfunctions are not tied to the particular equilibrium point, hence the model constructed from the principal eigenfunction does two things. One is that it is tied to the particular equilibrium point. Second is that it is the same dimension as the underlying system dimension. It's not a lifting model. It's not a model in the high dimensional space. It is a model in the same dimensional space. Now you use that linear model for which we know where that model is valid to design an MPC controller. Okay? So that way you can actually so kind of overcome some of the limitations of existing Koopman-based control design, especially MPC, to which is actually aware of the fact that what are the limitations of that linear model, because trying to construct a global linear model from data is not realistic, or rather it's like a pipe dream, right? So the data is local, or so the model will also be, especially because the model is actually finite dimensional. It's not an infinite dimensional model. So there's no one-to-one mapping going from the state space description or going from the finite dimensional linear model back to the state space, because the model that you ended up constructing, linear model that you ended up constructing, is the finite dimension. Okay, so I think that's is not there yet in the literature. So if somebody wants to sort of pursue this direction, I think it's a very good way to actually contribute to this growing field of Koopman for control. So I think one of the challenges, I think one of the useful, one of the good applications of Koopman theory is for control design, right? Of course, there are other applications as well: model reduction, prediction, model comparison. But I think the control is one frontier for Koopman, and I think this is, I feel, is currently missing from this. And again, here in the second thing which I just described, where we are actually bypassing the model, I sort of presented this more as an algorithm. There is also there is further layers of understanding to this. There is further refinement to this, because here you're working with this principal eigenfunction, where the principal eigenfunctions are actually limited to a certain region. Hence, the optimal control that you end up designing, or the optimal value function that you ended up computing, is actually also restricted to a certain region, right? But we know that if I solve the HGI equation globally, I could get a global optimal control. So how do I get a global value function which is not actually restricted to a certain particular region? The way you do that is actually a little more involved, and I'm actually skipping that. I'm not going to talk about that in any further details. So basically, what the long story short, basically what it happens is that rather than actually using the principal eigenfunctions of the open loop system, one can use actually the principal eigenfunctions of the closed loop system, which is obtained from the Hamilton-Jacobi equation. So one can show that, and this is also sort of well known, that given a Hamilton-Jacobi equation, one can always associate a Hamiltonian system with the Hamilton-Jacobi equation. And a Hamiltonian system, the Hamiltonian system is the uncontrolled system. It's a closed loop system, or rather, the optimal control is sort of already inbuilt into the Hamiltonian system. So one could actually use the principal eigenfunction of the Hamiltonian system to do similar kind of things, not exactly the same thing. And that actually gives you a global approximation of the value function. So I don't want to sort of talk about that, because I think to talk about that, I need to sort of introduce a lot more, not just mathematics, but I think I need to provide a lot more background on um, the Hamilton-Jacobi equation, which I don't expect everybody to be familiar with. Okay. So, but if you guys are interested in learning about this, I have a recent paper on that. It's the title of the paper is When Koopman Meets Hamilton-Jacobi. So take a look at that. It's you can find it on archive. This will come in print in IEEE transactions, and it sort of tells you the connection between the Koopman theory and the Hamilton-Jacobi solution, which is how do you sort of bypass the model and directly jump to the value function approximation. Okay, so take a look at that. So the one algorithm that I presented actually is one. So this paper presents two different algorithms. One of them I already talked about. The second one, as I said, involves a lot more knowledge of the Hamilton-Jacobi equation, but you can read it if you want. I hope you enjoy reading this paper. Okay? But if you have questions, you can ask me if anytime later. Okay? So, any questions so far on what we did? Okay. I mean, in the afternoon, we can talk more about this. If you guys, like those who have been working on Koopman theory, those who have some experience with code, I can actually interact with one-on-one and can see if there are some opportunities for carrying this work a little further. Because I think there are a lot of ideas that we have discussed in this. I think some of this could be actually pursued to write some papers on. Okay? So the next thing I want to talk about is how to do this all this control design stuff in a dual setting. Okay, and this is also quite at least 20 years old, like work, or this work has been going on for last 20 years. I have some contributions on this. So let me tell you what the first main fundamental contribution was, and then it actually opens up a lot of things for the control design. And I think this was actually the first paper when we talked about how to use linear operators for control design, right? Because before that, nobody actually had, like, there were some papers, but they were very obscure paper on use of linear operators for control. So for the first time, we talked about this back in 2008 on how to use this Perron-Frobenius operators for control design. So the idea was, as which is now sort of very popular or very familiar, is that you sort of translate the control design problem from the state space to the space of functions. You design control in a space of functions, and then you sort of go back, right? But what really started was with this very simple observation, and I'll tell you what was the observation. Okay, and that was very eye-opening. And I think maybe some of you know that, but given that we spent so much time on talking about these two operators, I think this will be an interesting for you as well. Okay, so let's just look at a very basic problem of. So before actually even talking about control design, let me just talk about the problem of simple stabilization problem, right? Or not even stabilization problem, the stability problem. Okay, so let's say you have a discrete time system. Let me just put a title here so that we understand. So let's just look at a discrete time system with no control. Okay. Now, and let's say x equal to 0 is the equilibrium point of the system. Now, how do you check if this equilibrium point is stable or not? Using Lyapunov function, right? So if there is a Lyapunov function, so I'm not going to write down all the technical conditions for the Lyapunov function. It has to be positive, C1, and so on and so forth. I'm just going to just write it like this. Lyapunov function V such that V P of x is less than V of x, right? That's the condition, right? So along the trajectory, the V is decreasing, right? Everybody is familiar with this, right? Now, do you see a Koopman here? And that was actually the observation. This left-hand side is a Koopman because this is kappa V acting on x. Okay, and I can rewrite this as minus V of x has to be less than 0. So Lyapunov equation can be written as a linear equation in terms of the Koopman. Okay, now I can also do a little bit more. I say, oh, kappa V of x minus V of x equals to minus G of x for some G which is positive. Okay, some G which is positive. Right? Good. Now, and this was the starting point of the whole paper was and the discussion. And then now you can build on top of it. Now I can rewrite this. Now I can look at this as a linear inequality in the function space. So I can write this as kappa minus identity V of x equals minus G of x. Okay. Now, how do you find the Lyapunov function V of x? And that has been a challenge for quite some time. So how do you find this V? Now, does this formula actually tells me, like just rewriting this in terms of the Koopman operator doesn't give me any nice formula to find a V, right? It turns out it does. So you can actually invert the left-hand side because this is an operator. So you can write this in terms of the k kappa minus identity. Take the inverse of this. You can then write it as a what is called a resolvent of this operator. So you can write down this V of x as kappa inverse G of x. Okay. So this is basically what is called as a resolvent. Kappa. Okay. Now this. So this, the problem of so you know that yes, G could be any arbitrary function. Okay, right for the timing. Just like when you do the linear Lyapunov equation, you have A transpose P plus PA less than 0. You can always pick left hand side to be any minus Q, right? So the Q is like the G. So that's a parallel between linear and this. So now this, and now without sort of making a big fuss about this, this is actually an inverse of an operator, right? So if the maximum eigenvalue of this kappa is strictly less than 1, these are actually all one if and one leaf kind of a condition. So if system is, we know that if the system is stable, there exists a Lyapunov function, right? If there is a Lyapunov function, system is stable. That's the inverse Lyapunov function argument. And now, if the system is stable, then this kappa will have maximum eigenvalue less than 1 if and one leaf. If the maximum eigenvalue of kappa is less than 1, then I can take this, I can define this inverse. This identity resolvent is well defined. Basically. Now, what is the resolvent is? This resolvent, and you have seen this in maybe the geometric series. So this is basically nothing but I plus kappa square dot times G of x. Okay. So your V of x is nothing but summation k equals 0 to infinity kappa or n kappa of n times G of x. Okay, which is basically saying, maybe I should write it like this. Which is basically saying, what is this? This is nothing but G Tn of x, n equals 0 to infinity. Okay. So this is how you can write the Lyapunov function in terms of the Koopman operator or the resolvent of the Koopman operator. Of course, this is all basically an observation saying that, okay, look, we can write the Lyapunov inequality in terms of the Koopman operator and so on. But now I know that a Koopman is actually dual to the Perron-Frobenius operator, right? Now, can I write this stability condition in a dual form? And it turns out that I'm not going to do the proof, but so if there exists a Lyapunov function V, then we know that each and every initial condition will be attracted to the equilibrium point. That is, everything will go to the equilibrium point. Okay. Now there is a weaker notion of stability, which is called as the almost everywhere stability. It was first time introduced by Ranzov, and then we sort of took it and provided a operator theoretic interpretation of that. Like for example, let's give an example. So let's say if our system x dot is I'm going from discrete to continuous. In continuous time, it's easy to construct this example. X dot equals minus sine of x, right? So, and this x belongs to circle, right? So, how many equilibrium points are there for the system? X dot equals minus sine x. So, this will be like, let's say 0, 1. So, this is the vector field, right? Or maybe like this, right? So, how many equilibrium points are there for this? So 0 is equilibrium point, right? X equal to 0. What is the other equilibrium point? X equal to pi, right? Is x equal to 0, which one is stable, which is unstable? Which one is stable? This is a vector field, right? So this is negative, this is positive, so x equal to 0 is stable, right? Agree? So what does that makes for x equal to pi? X equal to pi is unstable, right? Good. So is x equal to 0 globally stable? It's not, right? Why? Because there is a x equal to pi. So if you start at x equal to pi, you will never get to x equal to 0, right? Except for x equal to pi, no matter where you start, you'll get to x equal to 0. So it is x equal to 0 is stable in sort of almost everywhere sense. That is, everything gets to x equal to 0 except for one single point, which is a measured 0 set. Okay. So this is an example of a simple system where you have an equilibrium point which is not globally stable but almost everywhere stable. Okay. Does that make sense? Right. So there is very small set of initial conditions which are not attracted to x equal to 0, and that set of initial condition is a very small set. That is, if you are on a one-dimensional, if the system is on a one-dimensional line, then the points are not attracted. If the system is on a two-dimensional plane, it's a two-dimensional system, then there is a line of, at most a line of initial conditions, or initial conditions which are at most on a line which are not attracted. So it's still a measure 0 set, right? So for a system like this, you will not able to find a Lyapunov function because Lyapunov is actually a very strict notion of stability. Because if you can find a Lyapunov function, that means your system is globally stable. So, but you would like to call x equal to 0 for all practical purpose to be stable because it's very, you don't want to call x equal to 0 as not globally stable, right? Because for all practical purpose, for all engineering purpose, I'm okay with missing few points, right? I don't want to sort of disqualify x equal to 0 as unstable because one point is not getting there, right? So from engineering point of view, I mean, x equal to 0 for me is stable. I mean, more precisely, it is almost everywhere stable. So would it be actually good to have some certificate which will actually quantify this kind of stability, which is almost called as almost everywhere stability. Okay, and the answer to that is yes. And that stability is given by the dual certificate of the Lyapunov function, which comes from the Perron-Frobenius operator. So the system is said to be this xt plus 1 equals txt with x equal to 0 as an equilibrium point is said to be almost everywhere stable if there exists a density. Okay, so rather than Lyapunov function, the certificate is called in terms of density function. If there is a density function rho of x, which is positive, and rho of x belongs to, it's a L1, it's an integrable function, rather than saying that it is is radially unbounded and it's a C1. Here, what we need actually is we need it to be a integrable function such that it satisfies. Now, this is interesting. It satisfies the following inequality. So, what is the inequality for the Lyapunov? Inequality for Lyapunov was that kappa acting on V is less than V, right? Where kappa is the Koopman operator. Now, the inequality that rho need to satisfy for it to be a certificate for almost everywhere stability is that the Perron-Frobenius operator acting on rho should be less than rho. You see the parallel? So we have this kappa acting on V less than V for all x. Now, for the almost everywhere stability, the inequality is simply obtained by replacing kappa with P, which is the Perron-Frobenius operator. So if you can find that rho which satisfies this inequality, then that rho becomes a certificate for almost everywhere stability. Just like V was a certificate for this stronger notion of stability, the weaker notion of stability or certificate for this weaker notion is provided by this equation. Yes. Rho is a density function. No, it's not a probability density function. It's called a density function. Rho is like a L1 function. It's just an integrable function. P rho is also some function. Yeah. Just like this is the way it is written is pointwise. We can write it also in a measure sense than it is. So this also you can say is almost everywhere. This inequality is true almost everywhere because this is all sort of in the almost everywhere sense. Yes. It's like contraction of the measures corresponding to the as defined using the rho. As a measure is contracting. So I mean, if you think about this dual certificate, what is happening is the following, right? So in the primal Lyapunov function, you are familiar with the Lyapunov function, interpretation of Lyapunov function as an energy function, right? So when you write down kV less than V, what you are saying is that energy is decreasing as you actually, energy is decreasing along the flow, right? This P rho less than rho, what it says physically is that the mass, like if you think in terms of probability density, where the rho actually is like the captures density, the mass is being accumulated towards the equilibrium point because everything sort of, if you think about like stability concept, right? So if you think the stability in a dual setting, think of you actually putting a mass in some region in the state space, right? Now, if the equilibrium point is stable, it will actually suck the mass. So what is happening is that with this certificate, what is this saying is that eventually all the mass, you put the mass everywhere, that all the mass is actually now being accumulated eventually at the equilibrium point. So that's why this rho is only defined everywhere except at the equilibrium point, because at that point, this rho will have a singularity because everything is sort of accumulates at the equilibrium point. Okay? And another way to look at the stability certificate, which I think is very interesting, is that when you say equilibrium point is stable, so one way to say something is stable is to say that, one way to say something is stable is that it is kind of attracting things, right? Another way to say something is stable is to actually say that everything outside of that equilibrium point is unstable. You see, everything outside that is actually unstable. So that's what this is saying. So it is not a notion of stability, but it is notion of kind of a transient. It's saying that if you outside the equilibrium point, things are transient. That things doesn't stay outside the equilibrium point. If you take an equilibrium point and if you actually take a small neighborhood of equilibrium point and look outside this small neighborhood of the equilibrium point, things don't stay outside a small neighborhood of equilibrium point infinitely long. That means the things outside are actually transient. So stability is of equilibrium point is same as the transient of the complement of the equilibrium point. Yes. It is also satisfied. Yes, yes. So because the density will in the V, what happens in the V? V actually goes to infinity as it goes to infinity, right? But the rho actually goes to zero as x goes to infinity. For the case when you're talking about unbounded state space, right? So if you think about the rho is like 1 over the V, right? So one of the way you can construct the rho is by taking one. So let's say, for example, I know a system which is stable in the traditional Lyapunov sense, right? Of course, it has to be stable in this weaker sense, because if it is everything is getting attracted to equilibrium point, then almost everything is also getting attracted to equilibrium point. So then what will be the density for that? The simple answer is that take the V and take rho to be 1 over V, and that works as a density. Okay. Of course, you can have one way, but not the other way, that you could have things like one could be almost everywhere stable, but not stable in space. So you can find a rho, but you may still not able to find the V. Okay. So, so anyway, so you see now, just like we have this resolvent formula for finding the V, this formula can also be converted to find the rho. Okay, and that was the sort of the duality, right? So this I can use to find the rho in terms of the I minus P inverse of some, let's say, rho 0 of x. Right, so this is again becomes summation n equals 0 to infinity P of n rho 0 of x. Right? And why these two are dual notion? These two are dual because K and P are dual. K and P are dual. Okay? So it is fine up till this point. Now, what is the advantage of actually using this versus V? Because we have been using V for so long. Now I'll show you why this is advantageous. Let's say if you look at a simple control design problem for stability, right? And I said that the control design problem for control design using Lyapunov function is actually a non-convex problem, because the problem is actually you want to find the V and the controller simultaneously. And then these actually cannot be found simultaneously. Okay, the co-design is actually non-convex. But if I now actually say I don't want to design controller which is stabilizing in the strict Lyapunov sense, but I want to design controller which is stabilizing in this weaker almost everywhere sense, how is that synthesis problem looks like in this density? Okay, so as I said, I think this is the condition for discrete time. This is the condition for discrete time. One can write this condition equivalently in the continuous time as well. So for continuous time system, if you have x dot equals f of x, what will be this equation look like? So kappa v. So let's just do it systematically so that you can see this parallel. Okay, so we have xt plus 1 equals txt. So in this we have kappa v less than v, and then you have the dual form, which is p rho less than rho, right? Now if you have x dot equals f of x, how does kappa v less than v looks like? The stability condition. think in terms of the, instead of thinking in terms of Koopman operator, think in terms of the Koopman generator. So how this condition we can write in terms of Koopman generator? So that will be LFV less than 0, right? Because this, what is LFV? Is partial V, partial X, f of X less than 0. That's exactly the condition, right? Now, what do you think will this condition look like? You just replace P with generator for the P, just like we replace K from discrete time to continuous time with the generator of the K. Similarly, we can replace P with the generator of the P. I mean, we so far haven't introduced the notation for the generator of the P. So let's just introduce that notation. I don't know what do you want to use, because I think this is what I said, that we will need this notation in future. So what do you want to use? By the way, what does this looks like? So this basically, this is just a notation. So this is basically saying that partial f, partial x, f of x less than 0, right? And this is the Koopman generator. Now this notation we could use is, let me use this J, rho less than 0. Now what is a J here in notation wise? It is minus gradient of f rho less than 0. If you look back at your notes, this Perron-Frobenius generator is given by minus divergence of f rho. Okay, it is same as saying divergence of f rho has to be bigger than 0. So that's the stability condition in a dual space, the almost everywhere stability condition. Okay. Now let's look at a control design curve, and then from there we can build to the. Now we already know, actually, we in this course of this, I mean, we have done how to do the finite dimensional approximation of K, how to do finite dimensional approximation of P, how to do finite dimensional approximation of LF from data. So those methods can now be used to construct the Lyapunov function or the density function from data for just taking a certificate. But as I said, nobody actually is interested in finding a Lyapunov function. I mean, Lyapunov function is not that interesting. We use Lyapunov function mainly because it is used for the synthesis problem. So it's the utility of Lyapunov function is not for stability verification, but the utility of Lyapunov function is in the designing the controller synthesis problem. So let's look at that. But nonetheless, we could still use this to compute Lyapunov function if you want to, okay, for some applications perhaps. And we already talked about how to compute the finite dimensional approximation of all these different operators from data, and those could be used now to compute the different objects from data. Now let's look at a control problem. So let's say if I have x dot equals f of x plus g of xu, right? This is my control dynamical system, control affine. Now the stability condition, a stabilization condition in the primal setting will look like, in the Lyapunov setting will look like partial v, partial x, f plus g u to be less than 0, right? And let's assume that u is k of x, is what I want to find, a feedback controller. Okay. Now, to find this u equals k of x and v, you cannot solve this problem because you see partial v, partial x is multiplying k of x. And we don't know how to get rid of that bilinear term. Okay. Now, if I write down the stability condition using this, see what happens. You get divergence of f plus g k rho has to be bigger than 0. So what do you want to do now with this? You want to find what? You want to find a rho, that's your certificate, and you want to find a k. You want to find them simultaneously. Okay. So you can rewrite this as f rho plus g k rho bigger than 0. Right? I still have a bilinear term where k and rho are multiplying, which are both unknowns, and rho is unknown. But I can do a change of variable. So I can define my k rho as some rho bar of x. And now I can now try to solve this for divergence of F rho plus G rho bar bigger than G. I can solve this now because now rho and rho bar are linear. I can solve this thing. This is linear and hence convex in with respect to rho and rho bar. I can find rho and rho bar which satisfies the inequality. And once I find rho and rho bar, I can get this K as rho bar divided by rho. So you can solve this problem now convexly. The stabilization problem can be solved convexly. And now each of these are actually, if you think about this term, this is the generator, the Perron-Frobenius generator for the F. This is the Perron-Frobenius generator for the G, rho bar bigger than 0. So we can parameterize the rho and rho bar with some basis functions, which are used in the approximation of this operator and this operator, and try to find the rho and rho bar. Once you have the rho and rho bar, I mean, there's one thing, when you're trying to solve for rho and rho bar, you have to impose that rho has to be positive, right? Otherwise, you cannot divide. So rho has to be positive. Once the rho is positive, that's a constraint. That's again a linear constraint, so it's still convex. You solve for this rho and rho bar under this constraint rho bigger than 0. Once you solve for rho and rho bar, you get your feedback controller as rho bar divided by 2. Okay? And this is very similar in spirit of how you do control design for linear systems using Lyapunov function. Right? There also you make a change of variables because the K and the P actually multiplies each other. And then you actually again do the same change of variables where you multiply K and P. Same thing is happening here as well. So you multiply the K and the P is now the rho. It is a certificate. So you multiply the K and rho and to get a new variable and solve in terms of this new variable. Okay. Any question? Now you can actually use this, take this thing one step further and design optimal control in the dual space. So this is actually a dual formulation, which is again sort of not very well known, is actually a dual formulation of the Hamilton-Jacobi equation. So just like I said, that this Koopman actually is there in the Hamilton-Jacobi equation. Now you can actually do a dual formulation of that, the control problem, and then you will see the Perron-Frobenius in the dual formulation. And again, you can use the finite dimensional approximation of the Perron-Frobenius and so on to solve the dual problem. Okay, for the control, for the optimal control. You want to you have any questions, or is it too much? Yeah, is almost everywhere. Yes. Feedback law will be I mean the feedback law again will be almost everywhere Lipschitz. Yeah, I mean these are happening on a major zero set, so all these operators also are actually on. I mean, so that's I will not. Yeah, those will not bother. Except for a major zero set, this is fine. And of course, these inequalities are all on a major zero set. Okay, I mean all almost everywhere sense. Yeah, just because I think we're dealing with functions, right? I mean even the Lyapunov, when you write down that inequality, although you say it's strict, strictly speaking, it should again be sort of almost everywhere. Nobody's going to able to verify it at each and every point. Mm-hmm. Unless, I mean, unlike things when I want to sort of do that, I mean, still these are still pointwise, right? These are still pointwise. These are not like in the integral or the L2 set in a weak form. These are still in a strong form, but in almost every way. Any other question? I mean, as I said, I'm not talking here about the finite dimensional approximation, I mean, the data-driven part, because that has already been covered, right? That we already talked about what is the LF, how do you compute the LF, and what to compute this LG, and so on and so forth. So, so whatever methods we have used to approximate the Koopman operator can be used to approximate the dual, and then those could be used to approximate this these functions, the rho and rho bar. So now let me quickly talk about this, how to do the optimal control, because I think this is the core of it, right? This is the fundamental building block. Because I think the main message I wanted to give you was that in the dual setting, you actually get this convex problem, which I hope it is clear now. Now you can like further extend this to do optimal control, and then this convexity basically follows because of the things that I just described you. Only a small thing which I feel is kind of interesting, which hasn't been kind of like um, I haven't seen papers actually talk about, like a lot of papers actually kind of talk about that uh, the optimal control problem, or the setting of the cost of the optimal control problem in the way I'm going to do it, right? So when you design this, when you're like when we actually constructed a cost function, right? So what you do in the optimal cost function is the following, right? So you have some state cost and you have some cost on a control, right? And you're interested in minimizing that state cost plus the control cost, starting from each and every initial condition, right? So given an initial condition where I start the system, I'm interested in finding a trajectory such that the cost is minimized starting from that initial condition. So what happens because of that is you get this value function v, which is a function of x, right? So it is telling me what is the cost if I find this value function, which is coming from the solution of Hamilton-Jacobi equation. What is the cost that I will incur if I initialize the system from that initial condition x, right? So that's the meaning of the value function, right? Now you can also think about this in a slightly different way, which is kind of in a major theoretic sense. So instead of saying that, oh, I want to minimize cost from each and every initial condition, what if I say I want to minimize the cost not from each and every initial condition, but from a certain set of initial conditions? So instead of talking about points, now I'm talking about a set. Okay, and that set can now be, I mean, set is just a surrogate, but you can now extend that and say that, oh, I want to minimize this cost from a distribution of initial condition, right? So I have some initial distribution. Instead of having initial state x from where I want to minimize the cost, I have some initial distribution of initial condition, which is characterized in terms of some function rho 0. That is my initial distribution of points. And I want to minimize the cost from this distribution of initial condition. So I'm losing the significance of each and every point, but I'm giving the value, or I'm associating the cost with a certain distribution of initial condition. Okay. Now, how will that cost function look like? So that cost function, again, you can construct exactly like the way we construct the cost for the regular optimal control problem. So the regular optimal control cost was qx of t plus u square of t dt, right? Over infinite horizon. This was my regular cost, which is actually the function of each and every initial condition. Okay. Now I say, now here, what is x of t here? X of t is a optimal trajectory. I mean, at the end of the day, it's an optimal trajectory starting from an initial condition x. So that is kind of missing from this notation, right? That is not signified. So maybe I could actually write this to make that thing little clear. So I can say phi t of x, but what is this phi t? Phi t is the trajectory of the closed loop system. I mean, there is a controller there. That's why you don't write it as phi t, because so if I have to be more precise, then I should write down phi t of x comma u. You see what I'm saying? Because the phi t is the trajectory of the closed loop system. So I need to have s comma u plus u square of t dt, right? Now I have this x, which is the initial state. Okay. Now I say that this is my cost, regular cost. I want to weight this regular cost with the distribution, initial distribution. Now the initial distribution I'm characterizing in terms of some density function. So this could be a probability density function or just density function, as long as it's a integrable function. And then do dx, and then do integration over. You see? So this inside cost without the spatial integration is defined for each x, but that each x has a weightage which is characterized in terms of the rho 0 of x, right? So for example, think about, I want to minimize the cost from only certain set of initial conditions. Let's say the set of initial condition is this. And what I will do is that I will pick my rho 0 of x to be, let's say this is my set A, indicator function of the set A, right? What that means is that if I take an initial condition here, the initial condition here could go to infinity. I don't care, because that is not there in my, that is not the point of my interest. I only care about the point which are in this region, right? I only care about this point in this region. So I'm not interested in sort of globally stabilizing or globally minimizing the cost function, but I'm only interested in minimizing the cost function with respect to the initial condition, which are only captured in the distribution. So the distribution could be like a distribution which is supported on the entire state space. In that case, you just get back to it. The distribution could be like a Gaussian distribution and things like so. This actually makes it a little more general, right? Now, this cost function will now be a function of the rho 0. Unlike the cost function that you have, which is a function of the initial condition, this cost function is the function of the distribution. Okay. Now, this is the problem that you want to solve. Rather than saying, because the reason we are doing this is because when you go to the space of densities, the point actually loses any meaning. They don't have any, individual point doesn't have any significance. What you can only talk about is the densities, ensembles of point. And that ensemble of point information is captured in the rho 0. Okay. That ensemble of point information is captured in the rho 0. So now you want to minimize this cost as opposed to the old cost under the constraint of the system dynamic. X dot equals f of x plus g of xu. Actually, I forgot to mention one thing, and I think that is very significant. And I think that is perhaps the most significant physical interpretation of the rho, right? So density rho, which was used in the stability. Should I go back, or maybe I could do it here? I think I can go back. That has to do with the fact that, so I told you that this the Lyapunov function has the physical interpretation of energy, right? What is the physical interpretation of this rho density? The physical interpretation of the rho density is actually the occupancy. Okay. So what do you mean by occupancy? Occupancy, it means that let me actually do this, and then I'll talk. So I will skip this derivation, because I think this is, I mean, although the derivation is beautiful, but you see this actually we can now play with the duality. Okay, we can actually introduce duality and then show that this cost. So one of the challenge in solving the optimal control problem, the way it is, has to do with the fact that, I mean, what is the optimal control problem? I mean, optimal control problem, if you think about it, is basically an optimization problem, but it's actually infinite dimensional optimization problem. Why is infinite dimensional optimization problem? Because of the time. Okay, and that's why in the MPC, when you do it over a finite horizon, you get the finite dimensional optimization problem. So the optimal control problem is essentially infinite dimensional optimization problem. So the challenge in this optimal control problem is coming because of this time integral. Okay. Now, this time integral can be actually converted to the spatial integration with this Koopman Perron-Frobenius duality trick, and it's also sort of related to this. Those who are familiar with the ergodic theory, where you actually can show that time average equal to space average. So these kind of tricks can be used to show that this cost function, this is the optimization problem. Okay, I'm going to skip this steps, and you can show that this problem can be rewritten using the duality as a following convex optimization problem, which is purely in terms of the space. Rho of x plus rho bar square divided by rho of x dx over x. So this is actually a doing or minimize or rho and rho bar subject to rho plus G rho bar equals rho 0. I'm skipping the derivation of this, but I'll tell you what this basically is. First of all, what are the optimization variables here? The optimization variables are rho and rho bar. Okay. Now this problem is actually convex in terms of rho and rho bar. Why is it convex? If you look at the terms, so in the cost, you have linear in rho, it's convex. The second term is quadratic over linear, that is convex. And if you look at the constraints, that are linear in rho and rho bar, and hence convex. So this whole thing is actually convex in rho and rho bar. Okay? So, so one can actually rewrite this optimization problem in terms of this new variables rho and rho bar as a convex optimization problem. And once you solve this optimization problem, you get your K as rho bar over rho. Again, this has to be solved under the constraint that rho is bigger than 0. Okay. So this is a convex formulation of the non-convex optimal control problem in the dual space of density. Now, you see, these are actually all this divergence of F rho is the Perron-Frobenius of the F. Divergence of G rho is the Perron-Frobenius for the G. Okay, and so this is where the Perron-Frobenius thing comes in. Now, as I was saying, I think I missed that physical interpretation of rho. So if I just look at this constraint, you see, this constraint is basically F rho plus divergence of G rho bar equals rho 0 of X. Okay. So what is this? So let's say if you actually solve this optimization problem for rho and rho bar and get this feedback controller K, what does this equation really tells you is the following. Okay, so it has a very nice physical interpretation. So what it says is the following. So imagine that you're putting some mass, initial mass, which is captured using rho 0. Let's say you are in a state space. Okay, you have some initial mass, which is captured in the rho 0 of X, and you want to go to the equilibrium point. Okay. This rho 0 is capture the initial distribution of your point. Now, if you design this feedback controller so that everything eventually gets to the origin. So all this mass actually been basically getting transported to the origin, right? Now, then when this mass actually moves, it actually passes through a different region in the state space, right? Okay, it'll sort of move in a different region in the state space before eventually getting to the equilibrium point. Okay. Now, this initial mass may traverse in some region, may not actually get to some other region. Okay. So there are some part of the state space which are been explored, some part of the state space which have not been explored. So how do you know which region are explored and which region are not explored? How do you know where, even further, some region are actually explored more compared to some other region? That means system, when it actually goes, like system trajectories, when they go from this rho 0 distribution of initial condition as captured in rho 0 to the equilibrium point, the trajectories may be spending different amount of time in different region of the state space. So let's say if I pick, I know that this trajectories are actually going in this region, passing through this set A and this set B. Okay. This trajectory is starting from these initial conditions. I'm kind of trying to make it easier for you to understand. I mean, but I think mathematically it may not be precisely correct, but I want to give you the picture, right? Nonetheless. So you pick all the different initial conditions, and then all these trajectories from the initial condition, starting from the different initial condition, will pass to a set A, pass to a set B before actually getting to this region, to the equilibrium point. And there may be some set C where the trajectory never actually gets to. Okay. Now, this trajectory may be spending more time in A compared to set B, and it's spending 0 time in set C. Okay. How do you characterize that? And this is exactly the safety problem, right? Because what it says is that set C is never traversed. That means the trajectories are never intersecting set C. So if I want to mix like if some set C is an unsafe set, I want to avoid some unsafe set. That means I don't want the system trajectory to go to the unsafe set. Then I would like that my occupancy in the set C is 0. Now, how do you capture this? So this information about how much time is spent in different region and how much and which regions are not traversed is actually in this density rho of X. Sorry, not rho bar, the rho of X. So rho of X is a density. So what it means, rho of X is a density, and it's actually not just a like any density, it's also called as occupancy density. So what it means is the following. So given any density, I can define a measure. So what does it mean? So take any set, let's say any set D, okay? Any set D, I want to understand what is the occupancy in the set D. So the mu of D is the occupancy. That means larger the value of mu of D, mu on the set D, more time the system trajectory is spending in the set D. If mu of D is 0, the measure on the set D is 0, that means D is never actually traversed by the trajectory. So how do you capture this mu? This mu is nothing but rho of X dx on set D. The density rho induce a measure, which is the occupancy measure. Okay, that makes sense? So that's the physical interpretation of it. Now, I don't know if you know, the safety problem again is a non-convex problem. That means if I want to design a controller to keep certain regions safe, that's actually a non-convex constraint. Now that becomes a convex constraint in this formulation. So let's say I want to design this stabilizing controller in such a way that I want to avoid certain region in the state space. Let's say a region is O, some set O. So what I would say is that I would write down that as a linear constraints. Let's say the unsafe set is unsafe set is O for obstacle. Then I would say that I will add one more constraint to this, saying that rho of X dx on the set O is equal to 0. So this is again linear constraint. And that's how it becomes a convex problem. So safety can also be incorporated, safety constraints can be incorporated in this framework very nicely. Okay. Because that rho has a nice physical interpretation. Just like Lyapunov function has a physical interpretation of like energy like function or a cost to go, rho has a physical interpretation of the occupancy. And this is useful when you want to do some safety problems for robotics, right? These are very, very common problems, right? So you want to design some path such that you avoid some unsafe set, you avoid some unsafe region, and you can do that using, I don't know, like you have seen this control barrier function stuff, right? So this is actually a dual of the control barrier function. So maybe tomorrow I will tell you about how to construct these functions, okay, to avoid for a motion planning problem. And these can be constructed analytically. So the beauty of this is, as opposed to the barrier function or as opposed to navigation function. So how do you solve the safety problem in a primal setting? You solve the safety problem in primal setting using so-called navigation functions. So what are the navigation functions? Navigation functions have this physical interpretation that these are like so imagine that you have some unsafe set and you want to construct a function, and you have an unsafe set, you have some initial point, you have a target point. You want to take the robot from an initial point to a target point while avoiding the unsafe set. What you construct are these navigation functions or the barrier functions. So what are navigation functions? Navigation functions are sort of like a attracting repulsion potential kind of function. So whenever you have the obstacle set, you sort of create a repulsion. The functions actually take a very large value and kind of repels the robot from getting closer to that, right? And whenever you have a target, you actually create a minima so that you can actually get to the target. The problem with that is that you are sort of arbitrarily introducing these attractions and repulsions, and then you create an undesirable local minimum. Okay, and what happens is that your system could get trapped into undesirable local minima, and that's why it's a non-convex problem. Now you can actually instead of actually creating the attracting and repelling potentials, or combination of attracting repelling potentials using navigation function, you can actually construct functions, density-based functions, which are based on occupancy. What you can say is that, oh, I want to avoid this set, I will make my density 0 on that set. Okay? Because if the density is 0, I'm not going to get there. So you can that way, and I want to get to the target set, I will make the density very large there, because that's where I want my mass to eventually accumulate. Everything sort of goes there. So by doing this kind of construction, using this kind of argument, you can actually construct these functions nicely, analytically. And then you can use them for path planning problem. And you can use them for path planning problem, not just in a static environment, but also in dynamic environment, like where the obstacles are changing, where the target is changing, and things like that, because you have much more handle on this function, and it has a nice physical interpretation. Okay? Beyond this attraction repulsion. And one of the problem with this repulsion forces is that you have to really make them very large, right? So whenever the potentials or whenever the functions are very large, you inevitably get into trouble. Whereas these actually, you don't want to make them large, you're actually making them 0. Okay? Rather than making them large, because you want to have 0 occupancy. And it has similarities with the barrier function in that sense, but the barrier function actually is based on slightly different, again, sort of based on the primal interpretation. But one can prove rigorously that these functions can be constructed, and we can prove rigorously that once you construct this function, then we can actually go from point A to point B while avoiding obstacles. A rigorous proof of that, right? Which is lacking in the primal setting. Okay? So yeah, I think that's very powerful. Okay? So we could use them for motion planning. Yes. Yes, I mean, there are some like different variants of this, but yeah, I mean, like the plane, I mean, the simplest case will be like, I know where the obstacles are, and then using the knowledge of the obstacles, the global information obstacle, to construct this density function, right? Of course, when you are actually, I'll talk about it tomorrow in more detail, but once you consider density function, then you only need a local information or density function to move forward, because these are sort of what you end up actually getting is actually a feedback controller based on the local gradient of the density function. Because you're only using local gradients, you don't really, technically speaking, you don't really need the global information of the obstacle, as long as you can actually sense the obstacles there are enough. But yeah, yes. So any questions? Okay. If not, then we can stop here, and we can meet in the afternoon for those who are interested in like I can have like we can have some one-on-one conversations, or we can have some group chats if on like some of the problems that you described yesterday. We can have a little more detailed discussion if you want to share something, if you want some inputs on any of these things. I'll be more than happy to talk to you. I hope that I mean, what I feel is that there is plenty of things still need to be done in this area, and if you are interested in pursuing any of this, I'll be more than happy to sort of tell you what's the next step. It's a logical next step. So yeah, with that we can stop.